This is the second module of chapter 1, the real numbers. Fundamental theorem of arithmetic. The fundamental theorem of arithmetic states that the prime factorization of a natural number is unique except for the order of its factors. The prime factorization of a natural number is unique except for the order of its factors. Consider the natural number 156. We will be finding the prime factors of 156. The procedure is this: we will be dividing 156 starting from the smallest prime number available. We know that the smallest prime number is 2. We will be trying to divide 156 by the smallest prime number, that is 2. So 156 is divisible by 2 since all natural numbers whose last digit is an even number is divisible by 2. So 156 is divisible by 2. The result will be 78. 78 is again divisible by 2, resulting in 39. 39 is not divisible by 2. So we will be checking whether it is divisible by the next prime number available, which is 3. We know that a natural number is divisible by 3 if the sum of its digits is divisible by 3. The sum of the digits of 39 is 9 plus 3, which is equal to 12. 12 is divisible by 3, so 39 is divisible by 3. When 39 is divided by 3, the result is 13, which is a prime number. So further factorization is not possible. So 156 is factored as 2 times 2 times 3 times 13. The prime factors of 156 contains 2 2's, 1 3 and 1 13. The only prime factors of 156 are 2 2's, 1 3 and 1 13. No other prime number will not be a prime factor of 156. No other prime number can be a prime factor of 156. But the order in which the prime factors occur in multiplication is immaterial. We know that multiplication is commutative. That means x into y is equal to y into x. So the order of multiplication is immaterial. 13 times 3 times 2 times 2 will also result in 156. So the prime factorization of a natural number is unique except for the order of its factors. Now consider the number 280. 280 is divisible by 2, resulting in 140. 140 is again divisible by 2, resulting in 70. 70 is again divisible by 2, resulting in 35. 35 is not divisible by 2. It is not divisible by 3 as well, because 3 plus 5 is equal to 8 and 8 is not divisible by 3. But we know numbers ending with 5 and 0 are divisible by 5. So 35 is divisible by 5, resulting in 7. 7 is a prime number, so further factorization is not possible. So 280 is equal to 2 times 2 times 2 times 5 times 7. See the prime factors of A and B. What is the common prime factor of A and B? The common prime factor of A and B are 2 2's. 2 2's are the common prime factors of A and B. By multiplying the common prime factors of two numbers, we will be getting the highest common factor of those two numbers. So the highest common factor of A and B is obtained by multiplying the common prime factors of A and B. Here it is 2 and 2, 2 2's. So HCF of A and B is 2 times 2. Now consider the multiplication of A and B. A times B is equal to the multiplying of these two numbers is equal to multiplying all the prime factors of both A and B. Multiplying the product of A and B is obtained by multiplying all the prime factors of A and B. See, this is the multiplication. This is the product of all prime factors of A and B. So we can see that in the product the common prime factors are getting multiplied 2 times. 2 times 2 is occurring 2 times in the product of A and B. To obtain the least common multiple of A and B, we only need to multiply the common prime factors only once. So if we remove the common, if we remove 2 2's from the product of A and B, we will be getting the LCM or the least common multiple of A and B. I have said in the product the common prime factors are multiplied 2 times, but in the calculation of LCM the common prime factors need to be multiplied only once. What is the product of the common prime factors? That will be HCF. See, then LCM times HCF will be the product of A and B. What is getting repeated is the HCF of A and B. So LCM of two numbers times LCM of two numbers will be the product of those two numbers. That is, product of A and B is equal to LCM of A and B times the HCF of A and B. As I have said, in the product of A and B, the HCF, that is 2 times 2, is getting multiplied 2 times. But in the calculation of LCM, the common prime factors, that is HCF, need to be multiplied only once. So product of A and B is equal to LCM of A and B times the HCF of A and B. Express each of the number as the product of its prime factors. Express each of the number as the product of its prime factors. We are given two numbers 3825 and 5005. We have to first we have to express 3825 as the product of its prime factors. See, 3825 is a number not divisible by 2. Next we have to check the divisibility of 3825 by the next prime number, which is 3. So we will be finding the sum of the digits of 3825. 3 plus 8 is 11, 11 plus 2 13, 13 plus 5 18. 18 is a number divisible by 3. So 3825 is divisible by 3. When we divide 3825 by 3, we got 1275. See, now we have to check the divisibility of 1275 by the number 3. 1 plus 2 is 3, 3 plus 7 10, 10 plus 5 15. 15 is a number divisible by 3. So 1275 is divisible by 3. When we divide 1275 by 3, we got 425. 425 is we have to check the divisibility of 425 by 3. 4 plus 2 6, 6 plus 5 11. 11 is not divisible by 3. So it is not divisible by 3. But it is ending with 5. So 425 is divisible by 5. When we divide 425 by 5, we got 85. 85 is again divisible by 5, giving the result as 17. 17 is a prime number, so further factorization is not possible. So 3825 can be written as 3 squared times 5 squared times 17. Now we have to express 5005 as the product of its prime factors. 5005 005 is not divisible by 2. It is also not divisible by 3, but it is divisible by 5 since it is ending with 5. And when we divide 5005 by 5, we got 1001. 1001 is not divisible by 5. Now we have to check the divisibility of 1001 by the next prime number available, which is 7. How to check whether 1001 is divisible by 7 or not? The procedure is this. To check the divisibility of a number by 7, we will remove the last digit from the number. After removing the last digit, we got 100. Then we double the last digit. The removed last digit is 1. We will double the last digit. When we double the last digit, we got 2. Then we will be subtracting 2 from the remaining portion. Here the remaining portion is 100. So we will subtract 2 from 100. The result is 98. If 98 is divisible by 7, then 1001 will be divisible by 7. But it is not very easy to say that 98 is divisible by 7 or not. So we will continue the same procedure. We will remove the last digit from 98, which is 8, and the remaining portion is 9. Then we will double the last digit, which is 16, and we will subtract the double of the last digit from the remaining portion, which is 9. That is, we will be subtracting 16 from the remaining portion, which is 9. The double of the last digit of 98 is 8. We have doubled it. Then we will be subtracting the double of the last digit from the remaining portion. The remaining portion is 9. So we are subtracting 16 from 9, giving negative 7. Negative 7 is a number divisible by 7. The quotient is negative 1 and the remainder is 0. So 1001 is divisible by 7. When we divide 1001 by 7, we got the quotient as 143 and the remainder is 0. Now we have to check whether 143 is divisible by 7 or not. So the procedure is remove the last digit. Here the last digit is 3. Remove the last digit and find the double of the last digit, which is 6. Then subtract double of the last digit from the remaining portion. Here the remaining portion is 14. So we have to subtract 6 from 14. 14 minus 6 is 8. 8 is a number which is not divisible by 7. So 143 is not divisible by 7. Now we have to check the divisibility of 143 by the next prime number available, which is 11. How to check the divisibility of a number by 11? The procedure is this. We will be finding the sum of the digits of the number, but one difference is that we will be considering the even digit as negative. So we will be finding the sum in such a way that we will be multiplying all even digits by -1, and then we will find the sum of the digits. Here the first digit is 1, the second is an even digit, so it is multiplied by -1, so 1 minus 4. Then this is an odd digit, so it is positive, plus 3. So even digits are negative and the odd digits are positive, and then we will be finding the sum of the digits, and we will check whether the sum of the digits is a multiple of 11 or not. See, 1 minus 4 plus 3 is 0, which is divisible by 11. So 143 is divisible by 11. So I will explain the divisibility checking of a number by 11 with one more example. Suppose we are given the number 1782. So the first digit is 1, second is 7, which is taken as negative, 1 minus 7. The third is 8, which is an in odd position, so it is taken as positive, and this is in even position, which is taken as negative. See, alternative, positive and negative, alternate positive and negative, positive, negative, positive, negative, then add the digits together. So 1 minus 7 plus 8 minus 2. 1 minus 7 is negative 6. negative 6 plus 8 is positive 2. Positive 2 minus 2 is equal to 0. So 1782 is also divisible by 11. Okay. When 143 is divided by 11, we got the quotient as 13 and the remainder as 0. So 5005 can be written as 5 times 7 times 11 times 13. Find the LCM and HCF of the following pairs of integers by prime factorization method. Find the LCM and HCF of the following pairs of integers by prime factorization method. The numbers are 336 and 54. First we will be doing the prime factorization of 336. See, 336 is divisible by 2 resulting in 168. 168 is divisible by 2 resulting in 84. 84 is again divisible by 2 resulting in 42. 42 is again divisible by 2 resulting in 21. But 21 is not divisible by 2. But 21 is divisible by the next higher prime number, namely 3. So when we divide 21 by 3, the result is 7, and 7 is a prime number. Further factorization is not possible. So 336 is expressed as 2 times 2 times 2 times 2 times 3 times 7. Now we will be doing the prime factorization of 54. 54 is divisible by 2 resulting in 27. 27 is not divisible by 2, but it is divisible by the next higher prime number, namely 3. 27 divided by 3 results in 9, and 9 is divisible by 3 resulting in 3. 3 is a prime number. Further prime factorization is not possible. So 54 is 2 times 3 times 3 times 3. Now what is the common prime factors of both of these numbers? 2 is a common prime factor of both of these numbers. So 3 is also a common prime factor of both of these numbers. The common prime factors are 1 2 and 1 3. We have 1 2 and 1 3, which are common prime factors of 336 and 54. Multiplying by the common prime factors, by multiplying the common prime factors, we will be getting the highest common factor of both of these numbers. So HCF is equal to 2 times 3, which is 6. Now we will be finding the LCM. The LCM is obtained by the LCM of these two numbers is obtained by multiplying all the factors of 336 with the non-common prime factors occurred in 54. So I have encircled the common prime factors. We know in LCM the common prime factors should be multiplied only once, but in the product we have seen that the common prime factors will be getting multiplied 2 times. But in the LCM, common prime factors is to be multiplied only one. But we know the product of common prime factors is HCF. That is why we got HCF into LCM is equal to product of the numbers. So what is LCM? LCM is product of all the prime factors of 336 times the product of non-common prime factors of 54. So LCM is 2 times 2 times 2 times 2 times 3 times 7. Up to here is the prime factors of 336. Now we have to multiply it with the non-common prime factors that occurred in 54. That is 3 times 3, 3 and 3. So this is the LCM. LCM is equal to 2 has occurred 4 times, 3 has occurred 3 times, and 7 has occurred 1 time. So the LCM is equal to 2 raised to 4 times 3 raised to 3 times 7. 2 raised to 4 is 16, 3 raised to 3 is 27, 7 is 787 as itself. Now 16 times 27 is 432. 16 times 27 is 432. Use the Vedic mathematics method to multiply. 6 times 7 is 42, carrying 4. 1 times 7 is 7. 6 times 2 is 12. 12 plus 7 is 19. 19 plus 4 is equal to 23. carrying 2. 1 times 2 is 2, 2 plus 2 is 4. So we have got 432. 432 is multiplied by 7, resulting in 3024, 3024. This is so the final answer is 3024, 3024. This is the LCM of these two numbers. We have 336 is equal to 2 raised to 4 times 3 times 7, and 54 is 2 times 3 raised to 3. HCF is product of least power of common prime factors. The power of 2 in 330 in the factorization of 336 is 4. The power of 2 in the factorization of 336 is 4, and the power of 2 in the factorization of 54 is 1. The least among 4 and 1 is 1. Similarly, the power of 3 in the factorization of 336 is 1, and the power of 3 in the factorization of 54 is 3. The least among 1 and 3 is 1. So we have to multiply 2 raised to 1 times 3 raised to 1, which will be the HCF. We know 2 raised to 1 is equal to 2 and 3 raised to 1 is equal to 3. So HCF is equal to 6. And the LCM is equal to product of greatest power of common prime factors and non-common prime factors. Here we have only one non-common prime factor, which is 7. Now we have to find the product of greatest power of common prime factors and the non-common prime factors to get the LCM. So we have to multiply 2 raised to 4 times 3 raised to 3 times 7. We know that the power of 2 in 336 is 4 and power of 2 in 54 is 1. So the greatest is 4. So we have to take 2 raised to 4 times 3 raised to 3. We know that the power of 3 in 54 is greater than the power of 3 in the factorization of 336. So we have to multiply 2 raised to 4 times 3 raised to 3 times 7, which will be the LCM. LCM is product of the greatest power of common prime factors and non-common prime factors. So the answer is 2 raised to 4 times 3 raised to 3 times 7, which is equal to 3024. That is 3024.